Yes, okay. And I will share my screen. Can you guys confirm if you can see my screen? Yeah, very good. Okay. So, of course, guys, don't forget about the wiki. I'm going to give you a small lecture. I placed this small lecture inside the wiki already. This is in the documentation, embedded programming, and it's here, AVR C introduction. So in case you want to go back to the lecture, you can always go and click over here. Okay, so. So first of all, guys, in this case, we are going to use the C language, but this C language is specific for a specific architecture, which is the AVR architecture or Harvard architecture. So basically, many of the Arduinos have this underlying architecture. And for this architecture, as Neil was mentioning yesterday in the lecture, there are all kinds of C libraries that can be used to easily interface the microcontroller. One thing that is worth to mention for who wants to dig deeply into programming is that once you start programming in C, you can not only use, as Hamid mentioned before, the Arduino IDE, but you can also use a lot of different editors. So you can range from just like simple or a little bit more advanced text editors, which can be like brackets, atoms, Sublime, Notable++, and so on. Or you can go to what we call integrated development environments. In this case, you already know the Arduino IDE. But if you start running or writing like a code that is quite long and you need some, let's say, additional features, then you could go to this like Atmel Studio or, for example, Eclipse or Xcode for macOS, because they're going to have very nice integrated features that you could use to make your life easy. For example, let's say that in your Arduino code, you have many variables, and you want to change the name of this variable that you have duplicated maybe 1,000 times. If you use such editors like Eclipse or Atmel Studio or Xcode, you can do what we call refactor your code. So you can like rename just one variable, and all the other instances of that variable will be renamed as well. And this also across maybe different files. So once your program becomes very big, then you can work with those. I think those are a little bit of an overkill for Fab Academy. But for example, just I finished to install this IDE, Eclipse, which is quite easy to use also with Arduino. And maybe we can quickly look just one refactor function. Another easy functionality that they have is like the fact that they will check the code like in real time. Yes, I was making this simple Arduino sketch, so you still have here the void setup and the void loop over here. And here I created this simple variable. And then, for example, if you do right click and you press on refactor and then rename, then this is going to rename all instances of this variable with a new name that you are putting here. So this is particularly useful when you have a lot of variables. Another useful functionality is that if you make a mistake, like you forget, I don't know, the semicolon at the end, or you remove one parenthesis and so on, you don't need to compile the code. This shows you like instantly what is the mistake, or tries at least to show you what's the mistake. So therefore you can quickly check and go back and so on. So I will also check for like unused variables to save resources. And in some cases, it can even autocomplete the code. So you write like a variable name, okay, this is var or var2, var3, and so on, similar to the tab command in the git bash that you have in your console. And then from here, guys, you can still play your code, so upload it to the Arduino and so on. So this is just to give you a simple idea about other editors. So I think somebody was a little bit curious before, like what is happening under the hood, so of the Arduino IDE. So what will happen to your code, like the code that Hamad was showing you before, or the code that you will write in the Arduino. So what will happen is that this code is going to be translated in C, and you see these blue blocks are still a stage where the code is still readable, human readable, and you can still change it and adapt and so on. Then this code is going to be translated in assembly. Here is written that is readable, but I'm telling you it's really difficult to read because it talks about like accessing single slots of memory with hexadecimal codes and so on. And then you have the machine language, which is the hex file, the binary code, which is completely unreadable. So in this case, what we're going to do is we're going to skip the Arduino programming language, and we program the microcontroller directly in C. In this case, we still have the possibility to use some libraries, which are these AVR.h libraries that have been developed on purpose from also here a huge community and the manufacturer itself to easily program the microcontrollers. So this is the structure of a C program. You will see that there is no setup, there is no loop over here. There is mainly what we call the principal function, let's say the main function. That is the function that the microcontroller will execute first. So this main function is a very standard function. You will find it like in a lot of different languages, in Java, in C for computers and so on. And it contains basically the code that you will execute at the beginning. So when the microcontroller will be switched on, you don't execute the setup, you execute the main. And the main, guys, doesn't have any loop by default. So it's just like one function. So I think, William, you were asking before, okay, I just want to execute one function once and that's it. And that's the case of the main. Unless, of course, you put inside a loop, like a while loop or a for loop that runs continuously, like without stopping. In that case, it can be run continuously, or you have the call of another function. And inside this other function, you also have another loop that will make the microcontroller stop and execute this function, and so on. So similar to the Arduino IDE, we also have like a section before setup and loop. In this section, you can, again, declare global variables. As Ahmed was mentioning before, these variables can be accessed from any of the functions. You can have the link section, which means you can like link other libraries, like include, software serial, and so on. You could have a documentation section, which means that here you write a small comment that describes the file that you're making. So you say, okay, this file takes care of the serial communication, for example, and so on. You could also have definitions. So definitions are for variables that are not like changing over time, but they will stay constant and fixed during the whole execution of the program. And then after the main, of course, you could have multiple functions. So this is the way that you can declare a function. I think Hamad was already explaining you quite well at the beginning. What's the signature of the function? So the signature of the function is this first row here of the function where you define the specification of the function. So the first term is actually the data type that you want to have returned. It can be void in case you don't want anything. It can be int if you want an integer. It can be float if you want a number with a comma, and so on. And these two over here are the parameters. So those are the input parameters that the function needs to be able to work. In this case, this function just does a multiplication, and then it needs two terms to execute the multiplication. And then the result of this is stored in an int variable, that is called result, and then with the keyword return, you return the result. The way that you could use a function, it's actually like just by calling it. In this example on the right side, you have just a function that does not return anything, and that prints hello from the function. And then this one can be called directly by using hello here inside the main. So it's like that you, instead of writing this hello over here, you just write this whole block of code inside the main function. So whenever your code becomes bigger, bigger, and bigger, is really recommended to split the code in functions and to assign to a specific function, like specific block of functionality, specific block of like modularity for your code. So I think till now we didn't see anything completely new, and also in this slide we don't see anything completely new. Because you might remember that this way of addressing the pins, so like this, for example, PC6 or PD0 or PB4 or PB3, it's already in the datasheet. But what's new in this slide is actually the translation between the Arduino pin mapping and the actual pin mapping that comes from the manufacturer. So in the bootloader file, the Arduino developers define this digital pin 0, digital pin 1, these definitions here that are on the outside of this image, like analog input 5 and so on. They did this as a simplification for programmers to select specific pins. So in this case, if you want to select the pin, digital pin 0, you just write 0 and you have the pin 0. Or the left pin was, for example, pin number 13. But in reality, these pins in the manufacturer datasheet are labeled in a different way. So for example, we will see that digital pin 13 is called PB5, and analog input 1 is called PC1. So I don't know if you remember from one of the previous lectures that we were looking briefly at the datasheet, and we were giving to these pins some definitions. So in this case, the PC6 is port C6, or PD0 is port D0. So a microcontroller port in the AVR architecture is a set of 8 pins. So in this case, we will see that the ports will go from PX0 to PX7. So for example, if you take port B, it goes up to PB7, and then it has PB1, PB0, PB2, PB3, and so on. So we start from 0 and we end to 7. So this is actually not a coincidence, because to work with these ports, we have to address them. So we have actually bytes, and inside these bytes, we have to identify which one of the 8 bits corresponds to this specific thing. So what is important for me is that you are able to identify which pin has which label and belongs to which port. So for example, this pin 28 here, that is the analog inputs 5, is actually PC5. So we will see that these labels are very important to address them then in the program. So, guys, give me one moment that I shut down the fan that makes a lot of noise. So when you want to work with the AVR C library for programming in C, your microcontroller, you should be aware of the registers. So you might remember from Neil that the registers are actually like small slots of memory that are inside the microcontroller itself, inside the CPU part of the microcontroller. In the case of your PC, these registers are inside your CPU. There are some specific registers in the microcontroller, in the AVR architecture, that will allow you to manipulate the pins. So we can actually recall those the way that we were using pin mode to set the pin as inputs and outputs, all digital write, for example, to set one pin as to set the outputs of one pin as 0 or 1, for example, or even to read the state of a pin. So you can set a pin as inputs and read, for example, if button has been pushed and so on. So guys, there are many registers in the microcontroller. Those are the most important. And I hope that at the end of this lecture, you get the meaning of each of those. So in this case, the first register is called Data Direction Register, or DDR. In this case, X is relative to the port. So it can be DDR C, DDR B, DDR A, and so on. And these data direction registers, it's actually defining if you want to use a pin as input or a pin as output. So in this case, it's the equivalent of the pin mode. So when you do pin mode, like pin number 13 high, it's equivalent to set the bit as 1, for example, to set that pin as output. So then we have the port, that is the pin output register. This one defines the status of the output. So if you have the LED, for example, pin mode is high, and then you can say digital write high or low. And then in this case, this sets the pin as 0, so the LED is switched off, or 1, the LED is switched on. And the pin input register is then the other one that we use to read the status of a pin. So it's the equivalent of digital read. So digital read can be high or low in this case. Okay, so till now,
before you go on,
yeah.
So just trying to recap what you just were talking about there, these different things, DDR, pin, and port. We would use those to read the data coming in off the pins, or to set the pins to be able to read.
So the DDR is actually setting the pin as inputs or output. Only the first register.
So that's DDR sets the pin to be either input or output, correct?
Yes.
And so for each one of the ports, there are 4 ports, right? Or however many there might be. There's an A, a B, a C, a D, whatever. So then we'd send a byte, and there are 8 bits obviously in that byte. And then we would set for each one of the ports, we would say, okay, port A, channel 1, we're going to set that for input. Port A, channel 2, we're going to set that for output. And then we'd have a series of zeros and ones in that bit, which would make a number. And we could write that to the DDR for channel A. Is that what we're going to do?
Yes, you actually anticipated the next 4 slides.
Oh, sorry. I'll shut up. I'll wait for you.
But it's actually like that. The only thing maybe that needs to be added from your discussion is that if you set the pin as input, so this means that the bit is 0 in that specific slot. Then you can use the pin X, the pin register. So this one reads the input status. So if you set that pin as input, the pin X will tell you if there is 0 or 1, or if there is 0 volts or 5 volts.
Okay, at that pin.
At that pin, at that specific pin. Yeah.
Okay.
And port X is the opposite. So if you set the DDR of that pin as 1, so it's output, the port X, you can use it to set it as 0. So this means, for example, the LED is switched off, or 1, the LED is switched on. Okay. See better this in the next example.
Sure. And the X in these is all going to be the same. So X is A, B, C, whatever. And so we're going to have one of those bytes for every one of the ports that we have, correct?
So for example, if you see this this one over here, this is the Atitani 44 or the 84. In this case, guys, you don't have all the ports. You only have PA, port A.
Yeah, and
port
part
B.
of port B. Right.
If you go to the 328P, that is the one that you have in your Sasha kit or your Arduino compatible board. Then you also have, of course, PC and PD. Okay, so always read the datasheet to see which one is the port that you are referring to. But the concept is more or less the same as the pin mode and digital write and digital read. So this is actually the concept that William was talking about before. So in every of this register, you have like 8 bits. And as the pixel says, zeros on the right, 8 bits are making 1 byte. So in our case, what is important is that we are able to change each of these bits accordingly to our needs. And then every of these bits has also a position inside the byte. So if you see this one, we divide in lower nibble and upper nibble, accordingly if they are the first 4 or the one from 4 to 7. And this number here defines actually the position of the pin. So if you remember, like we have here, I don't know, PB4, PB3, PB2, PB1, and so on, then this PB1, this 1, or PB2, this 2, over here defines the position of the bit inside the byte. And this numbering here, it's useful actually to set the pins afterwards. So let's have a look to the DDR data direction register settings. So I think we can quickly look at this one over here. So the initial value that you have in your data direction register, it's always 0. So let's say they're all set as inputs by default. And then here you see you have this numbering. So the pin number 7 here, or for example PA7 or PD7, is DDX7, so 7 is the position of it, and so forth for all the rest. So let's say that we have the port C. So we have our beautiful datasheet. We look inside the datasheet, and then we see the ports that we have. Here there is an image on the right side with the port C over here. And then using these different ways, these are all like example codes. You can set actually 1 bit as 0 or 1 bit as 1 and so on. So let's take, for example, this first line over here. So we have the port C. So DDR C contains all of those, so 8 bits. And then with this bitwise operation over here, this shift left operation, we say, okay, the DTC 0, so this means the bit in position 0, must be 1. Okay, 1 means that PC0 here will be actually output. And then you do the same for all the ones that you want as output. So as default, you have 0. So this means that if you don't touch the others are going to stay as inputs. So, and then if you write this, this means that the PC0 is output, PC4 is output, PC5 is output, PC7 is output over here. And this corresponds to the image that you have here. So you can do this in different ways. I prefer much this way because it's really clear. You have directly here the position of the bit that you want to set. But of course, you can do this directly in binary. So you can write 0B and then you have 8 bits. And then the position of this corresponds to the position of the ones that you want to have. Or you can even use like this way over here. So in position 4, you shift the 1, position 5, you shift 1, position 7, you shift 1, and so on. Or you can even write in X. So X is quite cryptical, is actually the conversion of this byte over here from binary to hexadecimal code, which is, I think, more complex. So I think it's just worth to mention the bitwise operators. We will not go very deep in this. They just do the simple Boolean operation that you can have between bits. So you have AND, OR, shift, and so on. I think what I recommend to you is to look some already made examples, like modify them according to your needs. And then if you want to go deep in those, we can look together. There are a lot of simulators online or calculators online that you can put like the bits and they will tell you the rules and the output and so on. So with this, we took care of pin modes. So as you can see here, pin mode is a little bit more complex than just writing pin mode in the Arduino IDE. And this is actually the port X. So in this case, if you set your pin as output, so in this case, if you set in the DDR register this pin as 1, then with the port X register, you can set the output. So you can say, okay, please send 1 to that pin, which means output 5 volts in the case of the Arduino, or put it 0, for example, so this means 0 volts. And the way that this is done is exactly the same as the DDR setting of the bits. What changes is just the label. So this register is called port instead of DDR. So you have port D or port B and so on. And here you have, again, the possibility to set up the bits with the shifts operators and the bitwise or with the labels like PD3, PD6, and so on, or just with the position, or just with the bits, or just with the hexadecimal code. Okay. So, and then you can see here, you set the DDR-C, these are outputs, port C, this is 1. So this means that in this ones in the outputs over here, you are going to have 5 volts, and when you have 0, it's going to be 0 volts. So you can change these statuses, of course. We will see a blink. So putting this to 1 or putting this to 0, it's equivalent of like having the LED on or off. And then with a delay, you can have the blink as the Arduino. Yeah, and then quite similar thing is for the pin X register. So this pin X is for the input. So if you in the DDR C have set that pin as 0, then you can actually read the value. So in this case, you don't set anything in this register. The value that is going to be read by the microcontroller will be placed in this register. So if you have a button and you push the button and this is sending ground to the pin, you will read in this register 0. If you push the button and the button is sending high, then you will read 1 from this registry over here. So, and then you can do, of course, some ifs. So you can do, okay, if pin C, so the all then port C input, it's equivalent to this 0B, 01. So this means, for example, PC6 has 5 volts on it. Then you do something, okay, for example, you switch on an LED or you set up an output and so on. Yeah, there are many different ways of checking this. This is the binary way of checking it. So it's just like brutal, just 0 and 1s directly over here. There are some functions that you can use, for example, that is bit is clear or bit is set. This is, I think, much easier because of the labels. So you say, okay, if in port D, the pin PD2, sorry, it's 0. This means, okay, you have to do this one. Otherwise, you can use bit is set, which checks that in PD2 there is 1. Okay, so you don't have to write the binary code over here. And, it's much easier like this way. Okay, I placed here a lot of links. Here you can really dig deep. My recommendation is don't get lost. Try step by step, do some simple examples about the C programming. I also added this link over here. This is the famous library I was talking to you before, the AVR libc library. And this contains all these libraries that we're going to use for C. And here there is the library reference, so you can see all the things, libraries that you can import and you can use, and you can find the counterpart of the Arduino library. So for example, the delay, here you find it.
I can go somewhere else.
In you can find it in one here. The labels, for example, you find them in avr/io.h and so on. The standard input outputs here, you have a lot of facilities to implement your serial. You have some mathematical function over here. So the principle is similar to the Arduino. The difference is that these functions are written and they are working in C. So they have much more complexity inside. Also, the parameters can be pointers, which are address of a variable. That is another concept of C. I'm not going to go deep in this, but there are many more functionalities, let's say, that allows you to go deep into the management of the memory or of the microcontroller and so on.
So before you go any further, just to understand where we are writing C code to be able to either read or write from the ports on the outside of the microcontroller. So basically, we're just looking to either output ones or 5 volts, or to what we could, I suppose, output zeros, or to read what's going on in there. So basically, what we're doing is just writing codes that are reading and writing those pins. Is that more or less a description of what we're just trying to do here? And so we're deciding which pins we can write to, which pins we can read from, and what state we're either reading or writing to those pins. That's kind of where you've taken us so far, correct?
Yes, because this is actually, so far, is the right term, because we can get much more deep in this. We can also look how to make the analog read in this, but I think it's really complex. So I'm showing you, let's say, simple set of instruments that you can use, let's say, to just accomplish the average complexity of Web Academy in this sense. Of course, you can go much deeper than that, and Neil will say, wow, if you want, because, for example, for the analog read, the concept is quite similar, because what you do is always like reading and writing registers. In this case, you have a register to define the sampling frequency. You have a register to define the resolution. You have a register that contains your data or multiple registers. So the concept is always the same. In this case, we just use it for digital input and output. But in the case of analog, you have many more settings and so on. So it's the same for PWM. It's the same for all the functionalities that you want to use from the microcontroller. You always read and write registers. But then the meaning of the register is different. In this case, it's just like input and output, like bare input and output.
So if I remember right, when we were doing this and we were looking at the data sheet, there's a whole series of very specialized things that the different pins do. So some of them are PWM, some of them are different things. We're not taking that into account here, right? Or are we?
In this case, we are taking into account that all the pins, all the ports are having digital input and output.
So they're just all the same. So we don't worry about the different assignments.
In this case, the functionality to have like digital read or digital write, it's implemented by default because it's very easy, let's say, electronically to implement this in all the. But then if you talk about the analog, of course, this is only in some pins. So therefore, you have to address that pin specifically with that register specifically and so on. So this case that I'm showing you is really the baseline, super generic way of like using just input and output.
So can we assume, or well, I guess we can't assume anything, but we can always set a pin. So I guess my question is, are all pins always digital input out pins unless we do something else? And is it by default every pin, or are there special cases like here, right, on your drawing here?
Yeah.
So all of these pins, we have access to all 28 pins. Can we set, as we've just done, we can set, other than the ground pins possibly, but we can set all of those pins to be digital pins. And then the extra things like the analog inputs, those are things that we can do alternatively, but we can always set a pin to be a digital. Is that correct?
Yeah. So basically, for the 328P or the AVR, it's basically correct that all the pins are digital pins. Okay. Because it's super easy to implement, as I told you. So all of those can be used as digital pins. Even some pins can be reconverted to be used as digital. So for example, the reset, if you reset just by unplugging the power, you can reconvert this if you set this in the fuses, which are the basic setting of the chip. Okay, you can tell, I don't want to use this as a reset. I want to use this as, I don't know, a digital pin. Yeah. But of course, the other functionalities are really specific. So for example, as you may remember, you have the analog, so that are these ADC over here. You have RX and TX, of course, are only like in specific pins. You have the crystal over here. You can say, okay, if I don't use the crystal, I want to use those as digital pins. But as a baseline, as like default, or the pins that have the digital functionalities. So you cannot get wrong on that. Also the analog pins. Of course, if you sacrifice an analog pin for a digital input and output, you remove the possibility to use it as an analog pin.
Same thing with the crystal. I mean, but I can't use any other pins anywhere else on the chip for the crystal. I have to use those two for the crystal, correct?
Right. Mm-hmm.
Yeah.
So your resources are limited. Please count which one do you need for which function.
Sure.
And so on. Yeah.
Okay, thanks.
Okay, I probably just was just able to answer my my own question, but could you go back to your slides, please? Bit further down to the one more. Yeah, that would probably do. So if I understand correctly now, the thing is that whenever I use one of those labeled pins on an Arduino, one of those pins will be connected to 8 pins in the microcontroller, because what it looks to me is that that those 8 bits that I send with every byte will be split up into 8 different signals that simultaneously enter the microprocessor through those 8 pins that are all labeled from D0 to D7 in the case of the D port.
I think the answer is the microcontroller manufacturer wanted to find a way to organize the pins. And because the basic unit that we have in computation are bits and bytes, what they did is they grouped 8 pins in what we call a port. Mm-hmm. So every port contains 8 pins. A port is identified by a letter. Port A, port B, port C, and so on. Inside a port that you can have 8 pins, each pin is identified by a number. So if you want to identify a specific pin, you specify the port, I don't know, port D, and then pin number 1. So therefore you have PD1. Mm-hmm. The other answer is those are like registers, are like very small slots, actually of 1 byte of memory inside the CPU of the microcontroller. And wherever you set this one, the CPU reads this continuously and modifies the status of the specific pin accordingly. So if you have, for example, this DDX4 over here, and the port is port B, and this is 0, the pin PB4 will be set as input. So you go back here, and you say PB4, which is here, will be set as input. Yeah, it's just a way of addressing. So in this case, you can see how the Arduino simplified this process because they just have numbers. You have from 1 to 13, for example, and that's okay. In the case of C or the microcontroller manufacturer, they have to think about how the hardware implements this. And the way that this is done is just by positioning different bits inside a register.
So to I think what Kai was asking in your slide, you were just showing a second ago, come down a bit.
This one?
No, the one that shows what a byte looks like with output. One more.
Yeah.
Yeah, here. So here, when we say write somehow to the port, and we write B1, 0xB1 to the port, do all 8 bits simultaneously acquire the values we've just given them?
No, so you can do different things. So if you do like this way, 0B and so on, you set all the register at once. So all the 8 pins will change the state.
Right.
You do with a shift over here, the shift is really easy and useful because you can change only that specific one. So you don't apply again the all 8, you just change that one that you want to change. So in this case, you have only this C0, C4, C5, and C7. You only change this 4. So that,
that would
guys,
be,
I recommend you to use this way of doing it.
so, but that's okay. So that is to define single bits. But I think what we were asking is this one here, if we send a byte, then all 8 of those ports acquire that information simultaneously, or is there like a delay between each one of the bits being set?
So this will be written like it's going to be simultaneously defined, but then I don't know inside the microcontroller how fast this is, or if this simultaneous or this sequential.
Oh, okay. All right.
Yeah.
But
So,
if it is,
okay, but one more thing. It takes me 1 byte to well, no, sorry. Let's begin the other way. Other than just grouping those or defining all those different pins into neatly confined groups of pins, it doesn't have any further meaning that we have the ports. The port ABCD is just a way to group to form groups for those pins. Is that correct?
yes, because they have to match to registers. And
Okay.
the registers cannot be less than 8 bits because you have byte as minimum, you know. So
Thank
because
you.
we use this,
Yeah, so that means that for every one of those groups, I need 1 byte to define for each one of the 8 pins that belong to the same port. I need 1 byte to define their input or output properties.
yes, you need 1 byte to define all of them at once.
Exactly.
But if
Okay.
you use this method with the shifts, you can just define 1 bit. So you can address exactly like only 1.
Yeah, perfect. And then last thing I was wondering, through which port do I send that byte? Because I'm just defining for every pin whether it is set to be input or output. So where do I send it?
So I don't know if I got correctly the question. If you see in this image over here, there is some kind of translation between the way that the manufacturer organizes the pin.
Yeah.
With, for example, I don't know, let's take pin number 13 that you know very well. So PB5, for example, is translated for the Arduino programming language or the Arduino hardware. So if you take the Arduino, there are the numbers written on it, to digital pin 13. So if we want to make a blink, then you know that you need to work with port B and you need to work with PB5. So that's the translation for you. And because actually this translation is, let's say, an invention of the Arduino guys. But everybody that programs these chips seriously for some, let's say, kind of real case scenario, real life application and so on, they don't use the Arduino like this, digital pin 13. They use directly to address the pin with the port organization. Also because this adds an overhead on the execution, because this number every time has to be translated into the port and then to the specific pin of the port and then to the bit. So every time that you write like, I don't know, let pin 13 and pin mode, all this execution has to be translated. And this slows down the execution of the code, blah, blah, and so on. So that's why if you write this directly in C, it's faster than writing it with Arduino. But on the other hand, it's more complicated.
Okay, no, but I was wondering, but I think I understood now. I was wondering if this byte that defines whether a pin is set to input or output has, well, it needs a channel to explain the microcontroller how to set the pins, but this goes through the serial port. Is that correct?
No. This is a register. A register is like a small memory portion inside the CPU. It's a small block of memory inside the CPU. Doesn't go to or anything.
But how does the code get there?
This is then done by this library, by this AVR library, that they further translate this in this specific assembly code and then binary code that goes back to the microcontroller. So basically what we are talking about here is that in this hierarchy or in this stage over here, when you program with the Arduino, you are here on the top. When you program in C, you are one level below this top. But still, this requires some translation. And then the code is able to access this specific register of the microcontroller. It's something super fast. You can think that the registers are so close to the CPU that you can write them maybe 1,000 times in a second, or much more actually, because they are being read and being set continuously in a very fast way. So you can consider them as a kind of super fast RAM memory, but the RAM memory is separated from the CPU usually. This is like inside the CPU. So it's like the neighbor of the calculator, the neighbor of the, I don't know, ALU of the CPU, the arithmetic logic unit of the CPU.
Okay. Yeah, thank you.
So
Yeah.
It's you uploading your code where you instructed to set those registers. But you could also instruct it to set this differently for like 20 million times a second.
Yeah. So your code during the execution can change this 20 million times a second or whatever. Yeah. Okay, guys. So
is it right here? Sorry, go back to your slide there. Is this exactly what I think the answer to Kai's question is? If pin C comes in as this, then the next statement is port C is equal to that, right? So this is for the output, but would you do something similar for the DDR as well?
Yes, of course. You have to. This is just a snippet of the code. Before doing this, of course, you need to set DDR C accordingly, so that this one, for example, PC6 is input, and then whatever you do with B is output. Whenever you have ones in translating B from hexadecimal code, is going to be 1. I think if you look at the example, it's going to be easy. I hope. So I prepared 2 examples to you. One is just a simple blink. I think we can quickly go through that. Can you see my screen, guys? Is the font size good?
Yeah, looks great. Can we find this example somewhere, or can you share a link?
I will upload them in the wiki. Give me a moment. Yeah, if the font is okay, I will just proceed.
It's fine. Yeah, go.
Okay. So differently from the Arduino, you need to define the CPU frequency. This is something that you have to consider if you have different boards. For example, I don't know, the Anaptitani boards with 8 megahertz and so on. And this is a standard label for the AVR libraries that defines like, okay, inside this variable over here, I will place this value that is the frequency. In this case, is 16 million hertz. Then you need to import this avr/io.h libraries. These are the ones that define these labels, these super useful labels like PB5, DDR, and so on. And then you have to include also this delay.h. This delay.h actually defines some functions that you can use. And in this case, these functions are similar to the delay that you have in the Arduino. So you can use this underscore delay underscore ms, and then inside this you put milliseconds, and this defines actually the number of milliseconds the microcontroller will wait. So in this case, we don't have our predefined mandatory function like setup and loop. We just have main. So this is the standard way that you write a main over here. And this int over here is for historical reason, because this int over here, it's traditionally like the value that the software returns to indicate to the operating system which one is the error. So if the main returns 0, then you don't have any error. But historically, if you return 1 or 3 or 4 or 6 or 1000, this corresponds to a specific like error code. So in our case, to make it finish correct, we return 0 over here. So inside the main that doesn't take any parameter, we define our code. So let's have a look again to our Arduino pinout, to our 328P pinout, and let's try to understand which pin we need to set up as output for the pin number 13. So if we go back briefly to the slides or to the data sheets, either way, so we see over here that the pin number 13 is PB5. Okay, so it's port B, pin number 5. So in this case, the first thing that we should do is to set up this as input and as output. In this case, as Hamad showed you, the LED, if you want to make it blink, is actually one output. So in this case, the DDRB register, the bit in position 5 should be 1. So if you look into the code, we use this shift way of doing it. We say, okay, in the data direction register of the port B, the bit that is in position 5 must be 1. So this means, guys, that we have actually set 1. So this means PB5 will be 1. So you can write here PB5 is set as output. Or you can say, okay, DDRB, it's equal to 0B, and then we have 7, 6, 5, 4, 3, 2, 1, and 0.
Do we actually have this? Because that you're saying DDRB has all you've done is set bit number 5 to 1, but you haven't influenced any of the other bits.
Yeah, by default they are 0.
Ah, okay. So DDRB so the program by default sets everything to 0, and then you've just inserted a 1 into the position 5.
Yeah, it's equivalent to this. So this is 0B, and then this is position 7, position 6, position,
I get that.
Position 4.
But, yeah, sure. So the only thing that was missing in my mind is that you haven't declared DDRB anywhere as a variable.
Because this is already
declared it already? Okay, thanks.
It's inside the IO library that makes your life quite easy.
So those things are all defined as 0 to start?
Yes, by default. Okay.
And my second question here, DDRB is equal to brackets 1, less than DBR. How do I read that out? Is that so that those left brackets, that's a shift left, you said?
They shift 5 position, from the position 0, and they put 1 there. So this is equivalent again to make like 0B, 0, 6, 7, 6, 5, and then you have 4, 3, 2, 1, 0.
Okay, but the word shift, I guess, is my problem.
3, 4, so starting 0, 1, 2, 3, 4, 5 here.
Yeah. My problem is with the word shift. So I guess I don't completely understand what that's supposed to represent.
It's actually like that you want to.
William, I think the way that I read it is just a twisted, an inverse way of defining a value or giving a value to this DDB5.
Yeah, no, I understand that. No, my problem is with the word shift, because I was just assuming there had to be a 1 somewhere that we were going to move along, which would then disturb everything else. But it doesn't do that. What this does is insert a 1 into the slot 5. Okay, so then that's fine. I understand that.
Look this example maybe.
Yeah.
So this is the register. This is the default register. Okay,
yeah.
Beginning. It's all 0, no?
Yep.
So if you say I put this DDRB, okay, as 1, what will happen is that from here, have this.
Really?
Yeah.
Wouldn't I have?
Yeah. Oh. You should set like this, sir. Maybe it's more clear like this.
Yeah. Okay. Right. Because the other one could have been anything. Okay. Yeah. Sure.
To make it quick. So then, if you shift every time you shift 1 position, or this is in position 0, then if you shift to position 1, you have 1 here and 0 here.
Oh, so this is what it's doing. Okay.
Yeah, and then here you have position 1 and 0. This is shift 3.
Yeah.
So we can write this is, I don't know, 0. Okay. And then here you have 5. You have 1. Sorry, here, and you have a 0 here. Then this is shift to position 1. This is shift to position 2. Blah blah. Okay.
Okay, but when I shifted that 1 across, so in the first code, the line above that, 1 shift 1,
Here.
what happened? Yeah, okay, so
The
in
rest
here,
will be untouched, of course. It's
yeah,
moving.
but well, okay, it's moving, but I guess my question was in line 14. Okay, we set 1 in line 12. That's fine. Now we say insert 1 into position 0. We already had a 1 in position 0.
Yeah, it's the same. Now this overrides the value that was before.
Okay,
Yeah.
so now in the second, in line 15, where you say 1 shift 1, you're writing in the bit position 0, you change that to a 0.
No, yeah. So
Shouldn't it have stayed a 1?
Yeah, you're right. It's just because I wanted to show you from here till here.
Okay.
If this was the one or before, then this stays like this, of course.
Okay.
So you don't change anything. You just put in that position.
Okay. So it's not shift so much as insert. Okay. Cool. Now I understand.
Yep. Could I also, as you just mentioned, that if you just define the DDRB as 1, this would mean that the bit 0 would be set to 1, right?
Yeah.
So if I would say, if I would define DDRB equal to 3, would that translate into setting bits 0 and 1 to 1?
Yes.
Yes, because it's hexadecimal code. So it converts from hexadecimal to binary.
Okay.
But then,
understood.
on this, you need to look online, like from X. I mean.
But if you did that, Kai, if you set DDRB equal to 3, then it will set all of the other registers to 0 and then 1, 1 at the end. Whereas if you do the code that we're just being showed now with the shift registers, the other elements of it are not being changed.
Yeah, no, it's not the shift register, it's just the shift operator.
No, the shift operator, sorry. But it means that all of the rest of those bits are not being changed. So if we have here, when you do your 1 left DB5, then all you're doing is setting bit number 5. Whereas if you give it the number, whatever that is that whatever DB, whatever that it would be, then you would set all the zeros as well as the 1 that you're trying to set. So this is a way of doing it without changing it. I got it.
Please just use these ones, because if you use the X numbers, you could mess up the other pins, you know?
Yeah, exactly.
Well, Daniele, there's so many ways to mess this up. Leave it to us.
We will mess it up by definition.
So guys, just very short, then you have a while that is, Ferdi, sorry.
Just a second, one thing that cleared this up for me a lot was a tutorial from AVR Freaks, and I placed it in the wiki right below. It's like the bit masks are something that Neil uses a lot, and looking at this one for half an hour, I think will clarify the whole thing a lot.
Okay, so let's finish this example, guys, because I think in 15 minutes I have to do another 2-hour lecture. So here we have a while. While 1 means, okay, it's equivalent to while true. So it runs forever. I don't know if this is a problem for you, while 1, but it should be easy. And then what we do is the following. So PMB is the output register. And in this case, we want just to set the PB5 as 1. Then we wait 100 milliseconds, and then we set PB5 to 0. And then we wait another 100 milliseconds, and we never reach this point because this while is forever. So the cool thing that you can do is you can compile this with the Arduino IDE, because the underlying libraries are actually exactly the same. So therefore, wherever you press compile, it's going to compile it anyway, and is going to actually check if you also have errors in the C code. And then once you upload this one, you're going to have your blink. So in this case, again, don't get confused by this shift operator. In this case, we want to say this is the output register. So if the bit in position 5 is 1, this means that the Arduino pin 13 is logically labeled high. Therefore, the LED is on. And if you set at 0, the LED is off. So if I will upload this to my Arduino, I knew that this was difficult and that you had a lot of questions, especially you, William. One thing about the C is you can go deep as much as you want, but also for the sake of like making this efficient for your life, I recommend you just to get the basic things like understood, and then the rest look some examples and see the way that they're done. If you want, you can still go to the, of course, to the datasheet and go deep.
One more thing about it, Daniele, the last line of the code, the return 0, is that necessary because it mirrors the another part, or is that just redundant?
No, it's just redundant. It's just because of this historical thing that I told you that they return 0. So this means like it's in, I don't know, there are some microcontroller where this can be debugged. And then this value here as a meaning. So if you are a programmer and you say, I read the specification of this microcontroller, if I return 5, this means I had a memory failure or a corruption in the flash memory or something, you know? Then this number will be useful, sorry, to the debugger, to the one that is programming the chip, to check what's the error. I think William was asking before, the microcontroller cannot tell you the error. And one way is, of course, to check it by uploading it, but some hardware they have, like some microcontroller, they have hardware debug. And this number can be in that hardware debug and can tell you, oh, this is the issue. The issue is this one or the other one, and so on. So, but of course, this one here will never be reached because while here is forever. So we'll never get out of this trap over here. Other questions, guys? Then the last 10 minutes, I will be ambitious.
We're all doomed. We'll never leave this loop.
Yeah, so I also made for you another example, guys, that I will upload soon, which is a simple button. So this is basically all the same at the beginning over here. And in this case, we set one pin as output. It's still the pin number 13 over here. And then we set another pin as input. So this is port D7, PD7 is actually the pin number 7 of the Arduino. And then with this one, and this I know that will let you ask like 1,000 questions, we set up the pull-up resistor for this pin. So this means that, as Ahmed was mentioning before, we can enable this from the microcontroller. And this is the way that you set up the pull-up resistor in C. So this means basically, okay, this pin over here, I set it as an input, but in the output register, I write 1. So it's the same that you do pin mode like input, and then you set this digital write, same pin as high. So it's exactly the same as the Arduino. So then what we do is we use this super useful function. There are many useful functions you can find in the links of the lecture at the end, which just checks for you a specific pin, a specific bit, if that one is 0 or 1. So this asks, okay, is the in the port D, is the PD7 0? If yes, then switch the LED on. Otherwise, switch the LED off. So, and this is the way that you do like a button. So guys, if you manage to do that, I think some students pass it just with a blink, but I think you should do something more. The blink is really almost not sufficient. You can play with the button and the blink just to make it easier, or you can I don't know, go deeper and read some analog data and so on. We will be always able to support you also in that, but I think in this lecture is quite over. Okay, guys. I will upload this soon. William, you can send me your 1,000 questions. No?
No, that's all right. I'm just trying to think of. I mean, I know this stuff, but I'm trying to think of everything that bothered me when I was first learning it, to make sure we all are clear and on the same page. So I'm all right with this, but I'm hoping that the interaction is useful to everybody else.
Yeah, I think, guys, as Freddie mentioned, there are like thousands of tutorials that you can find online on like how to make this maybe simpler than the way that I show. I try to find like the easiest way because I've seen like assignments being done in a crazy way, even in assembly for embedded programming. So for me, this way of labeling is the easiest one, but there are thousands of tutorials you can find online. Yeah, so please dig a lot of tutorials and check these examples and so on.
Thank you, Daniele.
Oh, thank you to you
Lecture.
guys. It was very, very nice. You know what? Because usually when I explain C, the students are not asking all these questions. And let me stop the recording now.